This is video number 2 of doing phase diagrams, and in this example we're going to look at a portion of a phase diagram that has both water and carbon tetrachloride, CCl4. And so you can see here the axes are labeled. We have temperature along the X, and we have pressure or water vapor or vapor pressure along the Y. I want to point something out that wasn't in video 2's example. Right here I have 101.3 kilopascals, and that represents the air pressure in atmospheric pressure in our example. Why it's important that we know what the atmospheric pressure, I always need to explain to my kids that, for example, water is not going to change from the liquid state to the gaseous state. In other words, it's not going to boil until the atmospheric pressure is the same as the vapor pressure of that water. And so that explains why a lot of times as you change the altitude as you travel, the boiling point of water is going to change. So if you're at sea level, we know that the boiling point of water is 100 degrees Celsius. But if we go, let me write that down, sea level. But if we travel up in altitude, so for example, let's go to a top of a very tall mountain, and we boil water there. It is going to be, I'm just really having trouble with my pen here. Hold on. It is going to decrease because as we travel up that tall elevation, the atmospheric pressure is lowering. That's why athletes have a hard time and have to acclimate to lower or higher altitudes with a lower atmospheric pressure. So it's going to be less than 100 degrees at a high altitude. And so you might sometimes see that, like if you're baking a cake and on the back of the box mix, it will have special instructions if you're at an altitude above a certain level, because you have to adjust for that lower atmospheric pressure, because that means that your boiling point is going to be lower. But anyway, so we have the atmospheric pressure here. So what does that tell me? Well, when I intersect, here's water, when I intersect right here with the atmospheric pressure, I know I'm going to have the boiling point. So if I drop down, we can see that the boiling point is 100, because 101.3 is standard pressure. It's what would be the pressure at sea level. If we look at our other substance, carbon tetrachloride, you can see it intersects here with atmospheric pressure at a lower temperature. So if we drop down, it's going to be somewhere around like 78 or so. So the normal boiling point of water is going to be 100 if we look at these questions here. And of carbon tetrachloride, it's going to be 78 degrees. What would be the boiling point of water if the air pressure over the liquid was lowered to 60 kilopascals? So let's not worry about it being standard pressure. Let's go to 60. So I'm just going to draw like a line. I know it's not very straight. I'm going to draw a line there. There's our new pressure. So if I find the intersection of water with the pressure and I drop down, I'm going to see it's probably approximately, where's water? Right here. It's approximately going to be about 82 degrees Celsius. Okay? And then if we come over here for the carbon tet and we drop down, it's going to be, for the carbon tet, which they don't ask, but it's going to be approximately 60 degrees for the carbon tetrachloride. Okay, so then they change it to 20 kilopascals. So let's go down here and draw a line across there. And we see the intersections right here for water. We drop down. So water is going to be about 60 degrees Celsius. I know they don't ask that in the question. They're just asking for the other one. But if we, nope, I'm sorry. Yeah, that is water. So if we go down here, sorry, I was looking at the wrong line. Look here for carbon tet and come down, it's going to be about, let's see here, about 30. So if we put here 30 for the carbon tet. What must the air pressure be over the carbon tetrachloride in water if water is going to boil at 50. So let me just erase what we have here so that we can see our lines a little better. So now we're going to change the boiling point rather than the temperature. So we're going, or the boiling point rather than the pressure. So here's 50. I'm going to come up and I'm going to hit the water line, and then I'm going to go over, and it's going to be about maybe 11 kilopascals of pressure. And if we look at, if we want, so they didn't ask about, the carbon tet's boiling point would be about 20 degrees, where water's would be 50. Okay, so the last one is going to go into other videos I'm doing, but I'm going to answer it anyways. It talks about intermolecular forces, and it says, although water has a lower molar mass, in other words, water is about 18 grams per mole, and I didn't calculate the carbon tet, but if I added carbon and 4 chlorines, it's going to be way more than water in weight. And it says even though water has a lower mass and it has a lower vapor pressure, why is water less volatile? In other words, if I had a beaker of both of these sitting out, the carbon tetrachloride would vaporize first. And it's asking why. It's heavier. You would think that it would be slower. But it has to do with their intermolecular forces. And so if we look at water, water's intermolecular force is hydrogen bonding, where carbon tetrachloride is nonpolar, so it's going to be van der Waals or London dispersion. And if we talk about, just quickly, I don't want to get into a long discussion about this because I'll have videos coming up. This is the weaker one, the van der Waals. And the water, the hydrogen bonding is the stronger one. So the cohesion between the water is stronger, and therefore it's going to take more energy to pull them apart and let them change from the liquid state to the gaseous state. And so that is why that occurs. Okay, so this is the second video of phase diagrams, and find me on the third one where we do some examples. You can also find me on TikTok and YouTube at Kim's Kim Chats.